All right, everybody. Welcome back to your favorite class. Yes, ME3005. How's my audio? Hopefully we can hear it loud and clear coming through. Got my headphones on and now I'm unmuted, so it should be all good to go. Right, so sorry about the technical difficulty last time. I was having an issue with my writing pad, and that's because I got a new laptop and didn't realize I needed a new driver for the writing pad. So should be all good to go now. I was in here playing around with it and testing it, and it works great. So we're going to start in on lecture material now then. No more syllabus discussion, no more sleeping, okay? Real stuff now. And today we're going to work on combined loading. So the combined loading notes have been uploaded to Blackboard, and I'm going to use the writing pad in sort of like the traditional lecture style. So I'll switch that over for you guys to see in the online world, and I'll follow along pretty closely with the combined loading notes that are on Blackboard. So if there are no questions, we'll just flip it on over here, and we'll get going. Okay. So all of you in the online world now should be able to see my writing pad, and also the people in the classroom can see the writing pad as well. So we're all kind of looking at the same sort of thing. Yes. Okay. Good. I'm getting comments in the chat that things are going well, so that's nice. So I got to like manage two groups here. You know, it's like online and in real life. So okay. So with that, the topic today is going to be combined loading. So I'll get rid of that. That was my test writing. Don't worry, you don't have a test today. Just my test writing. And so we'll talk today about combined loading. My handwriting with the writing pad is not the best. Hopefully we can still kind of follow along and track with the writing. I'll try to enunciate what I'm writing as well so that it's pretty clear. All right, so the topic is combined loading, and hopefully you at least went through a little bit of combined loading in your 2004 class. I know if you like took 2004 last quarter, it's kind of crazy. So we'll maybe start with the basics of combined loading and build up from there, just in case you didn't have a lot of good background with combined loading. So let's quickly review some of the things that we should have learned in 2004, and that is stresses in a beam, right? So let's quickly review. That is stress. And I think my handwriting will improve a little bit as the class progresses, just as I sort of get used to the environment again. All right. So remember, if we have loads on a beam or loads on any structure in general, that's going to produce stresses inside of the piece. All right. So loads on a structure will induce stresses. Okay. And the types of stresses that we can have inside of a piece can be normal stresses and shear stresses. So normal stresses are those which sort of act in the same direction as the applied load, and shear stresses are kind of across the face. Okay, so normal stress is the stress you feel when you wake up and we still have a pandemic. No, I'm just kidding. That's not normal stress. It's abnormal stress. Okay. So loads on a structure will induce stresses. Normal stress, it typically come from axial loads or bending loads. And the symbol that you're going to see for normal stress is typically the symbol sigma. All right, so that's how I'm going to draw my sigmas. Should be pretty easy to follow. All right, shear stresses then come from sort of transverse loads, which are across the face, and torques, which are applied to the piece. It's like flashing on the board behind me. It seems to like kind of like flicker. I don't know if that's the writing pad. Is that doing that in the online world too? Is it like flickering or not in the online world? It's just a projector? Okay. Never mind then. We'll just keep going. Maybe we'll get IT in here. All right, so shear stresses can come from transverse loads, which are sort of loads across the piece, or from torques. And so we're going to use the symbol for shear stress, which is tau. Okay, so this is tau, T-A-U. This is sigma, S-I-G-M-A. And I will bring in here kind of pictures of some of these sorts of things to help with a little bit of clarity. Right? My pillar of engineering education, clarity. So if you're good at drawing, maybe you can draw this. I don't know if I would necessarily try myself, but this is kind of the idea that I'm sort of talking about here. So we're looking at axial loads and bending loads, which are going to induce thermal stresses, and transverse loads and torques, which might induce shear stresses. So these are kind of the pictures you might have in your head, and we're going to kind of dive in on these, each one of these individually and with a little bit more depth. So let's start with our normal stresses and talk a little bit more detail about what loads and moments might induce normal stress inside of a piece and how we deal with calculating that given certain informations about the geometry of the cross-section and of the information regarding the load or moment that's applied. All right, so let's first go to normal stress and review. All right, so first is normal stress. And your normal stresses, like I said, can be axial loading or bending. And so let's do axial first. And again, the picture that you should kind of have in your head is kind of the picture that we have above, where you have sort of a circular cross-section beam kind of protruding back into the page. And we're going to apply an axial load to that particular beam. So I'll sort of draw that as an arrow kind of coming off the face. And this is a singular arrow that's going to be our applied load P. And so this applied load P is going to induce a normal stress kind of equal across the cross-section. And what is our equation of the normal stress that's going to be induced for this particular load? It's like the first one you probably learned in 2004. Yeah, yeah, P over A. Okay, so here the normal stress is sigma is P over A. It's just a load divided by the cross-sectional area. Okay, where P is the load and A is cross-sectional area. Okay, so this is a normal stress that can arise from axial loading. So if we have this axial load P, we might consider the stress distribution in the cross-section here to be uniform with a value of P over A. So I'll do my best to sort of like draw this, but here we might consider the stress in the beam to be uniform over this particular cross-section. Something like this, where here this is your normal stress. All right, sort of uniform over that entire surface. Uniform magnitude. Kind of like this ease in switching of colors. It's kind of nice. I don't have to like get multiple markers and have my utility belt with my cloth on it to erase and all that sort of stuff. Okay, so there's your axial loading. Bending is probably the next thing that you talked about in 2004, and how bending loads or moments would induce normal stress inside your piece. So here now, let's consider our cross-section again. Of some circular beam. All right, and now we're going to apply a moment. And there's kind of two ways that you might see moments represented pictorially. One is by kind of like a curved arrow, something that might look like, if this is our sort of neutral axis for this particular piece, you might see a moment represented like this, where this is your moment M. And let's put a little bit of, let's put a coordinate system here. That's the word I'm looking for. It's early, so I did have my coffee. I'm still a little groggy. All right, where this M here is tending to provide a rotation about the x-axis, so we would label this as mx. Okay, it's this sort of like bending, trying to bend the bar sort of upwards in this particular situation. Right. You may also see it represented with a double arrow in the direction of the bending moment. So you can kind of think of like the right-hand rule curling your hand. If you thought about the right-hand rule and sort of bending this particular bar with this mx moment, your thumb is indicating about which axis the moment is being produced. So in that case, this would be about the negative x-axis, because by the right-hand rule, my thumb would kind of be sticking to the left if I'm looking at this picture. So you may see moments represented by this sort of like curved arrow, but I think in this class, I'm going to try to stick with what is the double arrow to represent moments. So this is also mx, and I would say that these two things are generally equivalent. So pictorially, you might see it as sort of this like curved arrow, or I'm going to generally stick to like the double arrow, okay, where this is sort of like emanating from the center of the cross-section. Both of these things would generally be equivalent in sort of a pictorial representation. All right. So here now, if we have a moment applied to our particular piece, then there's going to now be a stress distribution inside the cross-section as well, except now it's not going to be sort of this consistent stress in the cross-section, but it's going to have some distribution through the cross-section. And the equation here for stress from a bending moment is going to be equal to negative my over I. Okay, so something you also should have learned in 2004. Where here m is the applied moment. Y is the distance in cross-section from neutral axis. Okay, and I, here's the area moment of inertia of the cross-section. Okay, so when I talk about the variable y, that is the distance generally away from what is the neutral axis of bending. So here's your variable, little y. Right. So we can see here that this distribution, this sigma my over I, is a linear function. So we have y as the variable, and then the slope of the equation would be negative m over I. So drawing the stress distribution here, and this is going to be a little suspicious. Again, my Pictionary skills subpar. Everybody, we're aware of that now probably. If we wanted to try to draw the stress distribution, it would look like this. Oof, good luck. Where here we are going to have sort of compression on the top side of the bar. So we have this like compressive stress happening. And then on the bottom side, we have tension happening. Okay. So if you're kind of looking at the bar from the side, you might see, looking from the side, here's your z-axis, and here's your y-axis. You would see a distribution that looks something like this. Okay, where we have compression kind of on the top here, and we have tension sort of on the bottom. Right. So here, this distribution being my over I. This is something you should have talked about in 2004. Hopefully that was beaten into your brains. Rawr, bending. Right? So we could have these normal stresses coming from either axial loading or bending, or a combination of both. Hence the combined loading. Okay. So onwards with the shear stresses. And I think the first one I'll talk about is the more complicated of the two. Remember that shear stresses can be induced in our piece from either transverse loads or torques. And I think probably the most confusing of all of these like combined loading topics is the transverse shear. All right, so let's take a look at transverse shear, the equations associated, and how we sort of deal with this particular calculation. See if I can do this. Aha, yes. Okay, so again, let's take a look at our cross section. Here's our general beam. Okay, and unlike the axial loading situation where we had sort of loads coming right through the center axis of the cylinder. For transverse loading, we're going to have loads that are across the face, right? So here might be a transverse shear load. And if we, again, put axes on this particular guy, if this is X and this is Y, then we would say that this is some load that's across the face in the negative Y direction. So you might label this as like V sub Y, okay? But you could also have transverse loads across the face in the X direction as well. So you might see something across the X directional face as well, something like Vx. I'm going to get rid of this Vx because I just want to show one of the particular forces for now, but just understand that you could have transverse loads across the face in both general directions. All right? So when we have a transverse load across the face of a piece, we're going to have shear stress inside of the piece that is maximized at sort of the center, what I would consider this, you know, quote unquote neutral axis, or this central axis, this x-axis here as well. And the equation that we're going to have for shear stress is going to be something like tau is equal to VQ over IT. You guys have nightmares about this equation yet? Is this like sort of driving some memories for you guys? Yes? Okay. I got some nods in the classroom, so that's nice. VQ over IT, where V is the transverse load. Q is the first moment area, and we'll talk about what this is in a little bit more depth in just a second. I is, again, your area moment of inertia. Which is a geometric property of the beam. And then T is your thickness of the beam. Parallel to the neutral axis at a location of interest. Okay. How is the visibility in the back still? We're okay? Okay, good. Just want to make sure. Legibility, question mark, visibility, okay. Looks like we might have a question here quick in the chat. Oh, okay, we're good. Okay. So these terms are pretty explanatory. I mean, transverse load, that's pretty obvious. That's the magnitude of the load that's coming across the face. Area moment of inertia, that's, you know, a geometric property of the cross section. You can look this up in tables. T, thickness of the beam parallel to neutral axis. We're going to talk about this in just a second. So these two terms here, this T and this Q, tend to trip the students up most of the time. So we'll dive in on those a little bit more and just make sure that we're perfectly crystal clear on this. All right. So before we continue with talking about this Q term, let's just basically look at the distribution of the shear stress in the cross section. So if we have this general Vy, this transverse load that's across the face, that's going to create for us sort of the shearing stress across that face in that same direction. So we can consider like this shearing stress across this face. Shearing stress is usually denoted by like this half arrow, which is a little bit strange, but you don't quite get the full arrow. I don't know why, but that's kind of generally how shear stress is represented. Right. And this is transverse load. Okay. So now let's talk about these kind of more complicated terms, this Q and this T. Okay. So let's do Q, which is first moment. Or first moment area of inertia. It kind of has a lot of strange sort of names. If we're looking at some general cross section and we want to know the value of Q, let's say we have some general cross section. And let's say that the centroidal neutral axis of this particular cross-section is, I don't know, let's say approximately here. Okay. And we have some transverse load across this face. Okay, I'll just sort of draw it as this. We have this V value. And I'm interested in what is the shear stress at some arbitrary location in that particular cross-section. So let's just pick some arbitrary location in this cross-section. Let's call it here. And let's say that this is, I don't know, point, what do we want to call this? Point P. All right, this is point P. I don't like using P because people get it confused for like a load, but hopefully you can understand point P. All right, so the way that we attack understanding what the shear stress is at this particular location is the first thing we have to do is we have to draw sort of a horizontal line at point P, which is parallel to what is this neutral axis here. So the first thing that we do in our analysis here is we look at, okay, here's point P, and I want to draw a line that's more or less parallel to this neutral axis at point P. All right, so this is just kind of this line that we need to draw for ourselves to help us with our analysis. Okay, the width of this particular line at this particular location is the variable t. All right, so this width here is the variable t, which is the t in the equation that's up here. So when I talk about thickness of beam parallel to neutral axis at location of interest, that's what I'm talking about. I'm talking about generally this length here at this point P, okay? So now once we've sort of defined that first line, we're now able to actually calculate what our first moment of area is after we sort of define this line. And the way that we calculate the first moment area, Q, is with the equation here, y bar prime A prime, and I'll define each one of these things. Or A prime, here, a little bit cumbersome with the English, but it's the portion of the cross-sectional area that is above this line of interest T. That little variable T. Okay. So in this particular example, we've drawn this sort of red line which defines a line parallel to the neutral axis at our point of interest. We can now separate that cross-section into two areas based on that line, sort of this area above and the area below. The area that is the lesser of the two will be the area of interest here. So this area here is your area A prime. Okay. Y bar prime is the distance from the centroid of that area A prime to the location of the neutral axis. Complicated. Man, my head hurts. All right. So distance from neutral axis to centroid of A prime. Let's take a look at that. So in our particular example here, here's our A prime again one more time. It's this guy here. And if we're looking at the centroid of that particular A prime, well, the centroid of that sort of in the generally what would be the y direction, maybe that's, I don't know, right about here. Okay, centroid is usually defined by this sort of like plus sign sort of thing. Okay, so here is your centroid of A prime. A prime. And so the distance from the neutral axis to that particular centroid is the value y bar. So here's my neutral axis here, and the distance to that centroid is the variable y bar prime. All right, man, complicated. So we're going to do some example problems later on where we sort of hone this in and really lock this in for you guys to be 100% confident, but I want to take some time to actually just do the definitions and sort of show a general cross-section for this guy. Okay, so there you go. That's your first moment of area. And once you've calculated Q, then you can come back up here and actually calculate what the shear stress is at any particular location. As a reminder, if you're looking on the side of the cross-section, so shear stress from transverse load, and this will be a side view. Would look something like this. Okay, if you're looking at the side of the beam. Okay, you've got some load coming across the face. Here is the value of the load V. This distribution is going to be third order, and it's going to be maximized in the center of the cross section. Okay, so here's sort of like the center. This is your Z direction. And the distribution will be third order, kind of looking something like this. And let me actually blow that up a little bit, so I'm going to sort of draw this a little bit more clearly. No! Back. Baby, come back. Okay. Let's blow this up a little bit. And here's the distribution of the shear stress in the cross section. So no shear stress at the top and the bottom of the beam, right? So at the top and bottom here, tau is equal to 0. It's from your transverse shear stress. And here at the center, tau is maximized. Okay, so the center of the cross section has the largest transverse shear. And we would typically denote transverse shear again with these like half arrows. Okay, so remember that this distribution is the magnitude, but the direction of this distribution is actually like downwards across the face. All right, transverse loads across the face. How we doing? Questions? Questions? This is probably the most complicated portion, this like transverse shear loading. All right. Can I blow it up? Yeah, I could. I need to have my tools available. All right. So the last thing we're going to talk about is torsion. So let's do that now. So here now is shear stress from torsion. So again, we'll draw ourselves a little picture. Okay, give ourselves a coordinate system. X, Y. And let's talk about the last sort of application of load that we could have, and that is the torque. So we have some z-axis kind of coming off the way here. Then we can apply torsion and represent torsion in two ways. A lot of times you would see it as sort of this sort of curved arrow with a capital T. Here, this would be TZ, torsion in the Z direction. All right, so tend to sort of like curve the beam in. But in this class, I'm not going to use this like curved arrow. I'm going to use the double arrow notation. So when we think about turning this particular beam, my double arrow is going to point in the direction of my thumb by the right-hand rule. So if I was going to represent this same exact torque using a double arrow, I'd point a double arrow towards the center of this bar here. And this would be an equivalent TZ. Okay? These are the same. So it's just two different ways to represent torque. It's just what you might see by the picture is variable. Have you guys seen the double arrow notation before? Raise your hand if you have. Yes. Okay. All right. Good. I mean, I've taught this class a bunch of times, and like, it seems like sometimes like people just never seen it before, and other times like everybody's hand goes up. I'm like, what is going on? Like, do people use it or not? I don't know. I'm a double arrow fan. Okay, so there you go. So if you have this torque applied to the bar, you're going to have a torque at any particular location, which is equal to, a shear stress, which is TC on J. The general equation. T is the applied torque. C is the radial distance from the center of the bar. Not my best center. And then J is your polar moment of inertia. It's so cold. It's polar. Again, this polar moment of inertia is a geometric property. You can look most of the cross sections up for polar moment of inertia in a table. All right. So what does a stress distribution actually look like, the shear stress distribution? Well, it's a linear distribution where if you're at the center of the bar, this variable C here would be 0. And so at the center of the bar, we have no shear stress from torsion. And then it would be maximized when C is maximized. So when C is maximized, we're at the edge of the bar, the outer edge of the bar. So if we imagine a situation where we have sort of the center of the bar here, and we're sort of moving outward, this would be just generally like the R direction. And this could be, you know, axisymmetric about the center. You could have R this direction, or you could have R up here, or you could have R over here, or whatever. Then the distribution of the torque will be 0 at the center, and it will be maximized at the edge in a linear fashion. Okay. So it's a linear distribution, 0 at the center, maximum at the edge. And so looking something like this. Okay, so this is my shear stress tau, specifically from torsion. Okay, hopefully this has been reviewed. Okay, hopefully we sort of like talked about all these different types of moments and torques and loads that you could apply to a cross section and get a variety of these different stresses that develop inside of a beam. Okay. Now, before we talk about the analysis for combined loading, we have to talk about the method of superposition. And the idea of the method of superposition is if I have some bar or some piece that has a variety of loads on it, let's say I have an axial load, and I have a bending load, and I have a torque. Okay. The method of superposition basically tells me that I can look at the stress which develops from the torsion, independent of whatever stress that might develop from axial load, independent of whatever stress might develop from that bending moment. All right. So this is a pretty important concept in mechanics, in that it allows us to sort of do this combined loading analysis, where we look at each one of these individual loads separately, and then sort of add them up together at the end to give us a full stress state. But there's some restrictions on when you can and cannot use this, and so it's important for you to understand those restrictions so you don't make a mistake in your combined loading analysis. All right, so let's put that in writing. Okay. So if you have multiple loads on a beam, you're going to have to enact the method of superposition to get combined loading to go. So generally, you may have multiple loads, moments, and torques acting on a member. Okay. If so, you have combined loading. That's kind of our definition of combined loading. When you have more than one load, it's sort of acting to give you a sort of a complicated analysis and stress state. All right. So to analyze the stress in the bar accurately, you need to enact a method of superposition. All right. So to analyze correctly, need method of superposition. So the method of superposition relies on the beam not becoming plastic. Okay, so if you provide a lot of load, and you guys take material science class at this point, like Schaefer or Barnicki's class, where you like see an aluminum bar that gets like loaded to failure or anything like that? Some of you have, some of you haven't. Okay. So the method of superposition basically says that can consider loads individually. Oh, I'm not going to have enough space. For stress analysis. Then add them together to determine full stress state. Okay, so what I mean by that in equation language, because we're all engineers, we speak equations, we don't really speak English. We don't speak no good English. Okay. In equation form, you might sort of see this as the total normal stress on the piece is the summation of whatever stresses come from axial loading plus the summation of whatever stresses come from bending. All right. So sum up all the contributions of the axial loads, sum up all the contributions of the bending loads, add them all together, and that will be your sort of total stress, normal stress that's on that particular piece. Same thing with shear stress. Okay. The summation of the shear stress which might come from torsion plus the summation of the shear stress which might come from transverse loads. Okay, this is sort of an equation form what the method of superposition tells us. And we can just look at each one of these individual pieces alone and do the analysis on each individual piece alone, and then add them all up together at the end to get our full stress state. Okay, there are some assumptions here, and the assumptions more or less are that the material is linear elastic and isotropic. I'll say linear elastic, homogeneous, and isotropic. All right, so what are each one of these things actually mean? Linear elastic means that my load versus displacement relationship when I compress this or expand this is sort of a one-to-one ratio, meaning that if I put 100 pounds of load on this and it deflects 1 inch, that if I put 200 pounds of load on this, it will deflect 2 inches. All right, that's what it means to be a linear material. Right? Most materials that have not gone into the plastic regime that you possibly would know are this sort of behavior. There's some polymers maybe not exactly following that or adhering that, but metals mostly you're okay. Ceramics, you're okay. Homogeneous here, this term means that it's one consistent material, so you're not like composite material. It's one uniform material. And isotropic means that it behaves the same in all directions. So if I have a chunk of aluminum, if I load it this way or this way or this way, it's going to behave basically the same in all directions. Again, that's not quite the same as like a composite material, like a wood, for instance. So wood, if I load it along the direction of the fibers of the trunk, it's going to behave different than if I load it across the fibers of the trunk, right? So wood would be a non-isotropic material because it behaves different in different directions. So we have to make these assumptions because if we don't, then our method of superposition is not going to work out well. If you have an axial load that's causing you to become, put your material into a plastic regime, and it's not really accurate to add like the contribution of the axial load to the contribution of the bending load to really give you the full stress state. Okay, so that's your method of superposition, and that gives you that general equation that I showed there, which is the contribution of each one of these individual components can be added all up together. Okay. Now, I'll go maybe one more slide here and talk about sort of like the method of analysis here. So I kind of like showed you that each one of these individual things can be analyzed. What is the equation that's associated with each one of these particular loads and styles? But now how do we actually execute that at one particular point inside of the piece? Well, the way that we do that is, let's say you have some structure, some, random structure, and I might have some load here, some torque that's acting through this axis, some moment that's acting through this axis, etc. And I'm interested in what is the stress state at one particular point in that piece. Well, you sort of have to reach back to your static days, your 2001, and relocate all those torques and moments and all those forces to that one particular point of interest, okay? So when you're relocating forces to a particular point, you have to do things like force couple relationships to determine what is the equivalent force couple at that particular location so that you can do your analysis correctly, all right? So your method of analysis is going to rely on some of the tools in your static tool bag to get you back to a point of proper analysis. Okay, so analysis methods. All right, so what we want to do is identify point of interest. Then you want to relocate all your forces and moments to that location. Okay, and then execute method of superposition. All right, that's the English version. Now let's actually sort of draw pictures because I like pictures. Right? I'm a very elementary mind. All right. So let's consider an object. The world famous mechanics potato of Dr. Hart. Okay. Just random object here. And let's say it has a centroid at point O. Or let's just say point O is our point of interest. That's probably a little easier. Right. We might have a variety of other points on this object where forces or moments are acting. So let's say maybe I've got a force over here at A1, this point A1, that's acting like this general direction. And maybe I got some force over here at point A2, it's acting in this general direction. And maybe I got some point down here where I've got some moment that's applied. And let's just call this M for consistency, M3. Right? So let's say I want to do my analysis at point O. Well, I got to relocate everything appropriately to point O. So relocate to O. Okay, so if we get our potato here again, I've got to relocate my forces using force couple relationships. So here is point O. Once more. And I want to relocate the forces to point O using this force couple relationship. Well, to do that, I'm going to relocate that force, but that relocation is also going to give me an equivalent moment. So remember here that if I'm trying to relocate, let's say to this point here, this point O, that there exists a vector that points between point A and point O, so O1 and A1, and that's here. And that position vector here we can call capital R1. For those of you that haven't had me in class before, when I write vectors on this little writing pad, I usually put a bar over the top of the variable so that you know that it's a vector. So I probably should have done that with the forces here as well. These are all vector quantities because they have magnitude and direction. So let's be clear and do that here appropriately. So similarly, we have some vector that points from O to A2, which is like R2. And we have a vector that points from O to A3, which here is R. Okay. Now, if I want to relocate these forces appropriately, I relocate the forces like F1 and F2, 2.0. So again, here we might give ourselves like F1 and F2 being relocated appropriately. But because I relocated those forces, I need to account for the moment that is equivalent that I need to sort of carry over for moving that particular force. And the moment that's generated when I relocate those forces is the moment that is R cross F, right? So we generate a moment when we relocate those forces. Generate R cross F when moving. So I've relocated these forces, but I've also added an additional moment, which is R1 cross F1. If we kind of think about your little right-hand rule, R1 cross F1, maybe that'll give me a moment kind of coming out of the paper that is here, results, that is M1. So an equivalent moment is created by relocating that force from one location on the structure to point O, which is my point of interest. Same thing with the force F2. I've got to relocate that to point O and create an additional couple, which is sort of replacing. So R2 cross F2, maybe that's going to give me a moment here that looks this. M2. And M3, there is no, I can move that guy freely on the structure. So M3 just gets relocated as it is to point O. All right. So now I have this system of equivalent forces and moments. And I can either choose to do my combined loading analysis on all of these individual pieces. So let's say now enact the stress at point O is the summation of all of the forces. So it would be the summation of individual forces on the cross-section which they act, plus the summation here of this negative my over I. So I could look at the contribution of all of the individual forces here, on my relocated structure, and figure out the axial loads that come from those individual forces using that beginning portion of method of superposition. And I could also figure out the amount of bending contribution from these individual moments that I get by relocating them to point O, using this portion of the method of superposition. Right? Same thing with the shear stress. Okay, so this is summation of VQ over IT, which is your transverse shear contribution, plus the summation of TC on J, which is the torsional contribution. So this is sort of how the method of superposition works. That'll be it for today. I'll show some examples when we meet on Monday. We'll work through some examples really slowly first, just so we're kind of all on board with this general method of analysis and idea. And then we'll do a couple more on Wednesday to sort of bring it home and really lock it in. Okay, thanks for coming today. I resolved my technical issues, so I feel pretty good. Hope you guys have a great weekend.